All right, welcome back. We're going to kick off our afternoon with a lecture by Ethan Chi on how to clean up your code. This is a critical piece of the research process and one that often a lot of research groups and teams struggle with doing. And this lecture is intended to elucidate some of the best practices behind this process. So without further ado, Ethan, take it away.
Thank you so much, Pranav, and I'm really looking forward to giving this lecture about how to clean up your code. So today's topic is how to clean up your code for release, which might sound very simple on the surface, but there's actually a lot of very important components that impact your ability to make yourself clear, make your code easily available and understandable by the general population, and to make your code in a state that you yourself can come back to later and pick up where you left off without major confusion. Today, we're going to be trying to address three goals from low level to high level. Let's take a look. The first one is basic logging and communication practices. The goal here is to get results that you can easily understand and reproduce yourself later. The last thing you want is to be losing your code or to not understand what you took to get a very high result or good experiment. The second step is basic organizational practices. The goal is to write code that both you and your team can work with. Finally, the last step is to write a README. The goal here is to write code, write a README, create a repo that other people can understand. So not just you and your team, but the general public. Today, we do have a repo, which is available at this path. So if you're watching live, feel free to type this in right now. I will quickly paste in the link. 1 second. I will paste the link into Zoom. And if you're watching on a recording, obviously feel free to type this in right now at the moment as well. This code base represents a small example of machine learning code. It's obviously a mock-up. The data that's provided is not real, but I'm hoping that I can serve as a little small example of some best practices to follow when cleaning up your code for use. Let's start with number one, logging communication. So here's a common workflow. I wonder if this is, many of you, this might be familiar. I know that this is something that I struggle with when I first started writing machine learning code. The situation is as follows. You have a code base with a lot of sprawling code, probably 1 or 2 big files, and there's a lot of it. It probably hasn't been committed in 3 months, and it's not clear what of it is working and what of it is not. You change the configuration, you experiment. The only good way to do it is to navigate to line something or other and edit some constant. You just scroll through your editor and find line 42, and you change the batch size from 5 to 10. And if the experiment does well, yay, you get the terminal logs or print out some number, and you paste it into your Google Doc or into a spreadsheet or something. I've even seen magic commands pasted into your Notes app. Hopefully you don't do that. But the overall message is you don't want to be in a situation where nothing is quite pinned down. Why is that? Okay, so suppose, despite all these things, you're doing wonderful machine learning work anyway, and your experiment achieves state-of-the-art results. Excellent. Or maybe you achieve really good results and you're going to publish your project in your class, or you just want to figure out, what you did to get such a great experiment. But unfortunately, you have no idea what the nature of the experiment was that got you there. When you go back and read through your logs, they tell you nothing really about the exact configuration of the experiment. Even the experiment you did dump hyperparameters or something like that, you still may have no information about what exactly was in the code base at the time. The end result is disappointment, as you're no longer able to replicate the code and the hyperparameters that got you to where you need to be. So one option is, okay, I'm just going to be really defensive. I'm going to commit my code every day before every experiment, and that means that I'll never lose anything. Is this a solution, though? Although you'll never lose your code in this case, it's extremely hard to figure out which experiment led to which code. Sure, it might be technically possible to match it up, but it's really hard to do actual research in the sense that it's really hard to take some kind of input, like figure out how changing one thing led to another, or adding another hyperparameter led to increased performance. Another option is to use weights and biases. This is super common. Now your code is saved, things are reproducible, great. But it's still really hard to do the same thing, to understand the circumstance that led to one experiment doing better than another. Weights and biases is great, obviously, but it's no substitute for good experimental hygiene and practices. Here's a suggested strategy for reproducibility. The strategy is used throughout many research code bases online and can really help make sure that things are reproducible and clean. The way to do this is to make sure each experiment generates a coherent set of artifacts. These artifacts have to be separate from each other, and each experiment has to be separate, like stored in a separate artifact directory. The artifacts then might entail stuff like configuration, checkpoints, output files, the codebase itself. Importantly, we're not forcing people to scrape through the logs and do weird text processing to access the log performance. Rather, by dumping performance to files, it's very easy to use a bash script to extract like performance, accuracy, or other metrics that you might want to upload into a Google Sheet later. To put this into practice, and we'll take a look in the code base very shortly, each experiment is going to be turned by a config file. So sweeping over hyperparameters then is simply a set of configs. You can then just run like a really large set of configs, again, automating it using bash to just sweep over hyperparameters. Each experiment lives in a separate folder, including configuration, code, checkpoints, and results. And to get some results, you aggregate them using a bash command to produce some TSV, which you can then upload to Google Sheets and do whatever data analysis you might want. Let's take a look at the code. Of course, if you have any questions, feel free to ask some right now as we switch on to a code. Okay, so again, please open, if you haven't done so already, please open the GitHub link that I provided in the Zoom chat a little bit ago. This is an example of a code, a little code base that does some quick machine learning stuff. And it's designed to produce reproducible and be easily configurable in its artifacts. How does it work? When you execute the main function, we start by asking for a path to a YAML configuration file. These YAML configuration files are then loaded using, of course, the YAML library. If you've never seen YAML before, it's simply a way to add structured data into your Python program. YAML can easily be generated by, say, a bash script or any other script you might want. So looking at this configuration, it specifies important aspects about the experiment, like the path to a data file, the kind of model that we're using for our experiment, and some arguments you might pass to the model, as well as some metrics you might want to log about the experiment. The way this function works then is that we load the YAML arguments, and then we execute the code base with all the arguments passed to every function. For example, in our run experiment function, we might do things like loading a data set, getting models, getting metrics, and then training. In each case, we've passed this central args object to each of these functions. That way, each of the subfunctions can access any configuration that we passed here. For example, in the load dataset function, we simply use args data path to access the path to the original dataset. This means that things are incredibly easy to configure. If I want to change which dataset I'm using, I simply make another config file. Let me give you an example of how I might do that. Right now, I have boston.yaml, which tries to predict some data for the city of Boston. If I want to run, experiment at San Francisco, that's very easy. I make a new configuration file called data/sf.yaml, and I can just pass a different path. Now the experiment is running on San Francisco instead and can learn something different about the data. You can imagine how, on a larger scale, if I wanted to run a set of 15 or 20 experiments with 15 or 20 data sets, it'd be very easy. I just need to make copies of the same file and automate the process of replacing the data file. Another good example of what you might do here is automating model selection. A super common problem that people have is they're trying to change the model and they might write out explicitly in code, I want the model to have the following arguments. However, this leads to a lot of challenges in reproducibility because modifying the hyperparameters model entails just editing the code. This is bad because then you lose what hyperparameters made the model the best in the first place. Fortunately, there's a simple answer to this problem. We can actually define the model symbol in a structured way. So for example, here I've defined the model type as linear regression, and I've passed some arguments that get passed over to the model. Looking back at this code, there's a function called getModelClass4ModelType, which associates words like linear regression and decision tree with the actual names of these classes. That way, if I pass linear regression, we get back a linear regression, sklearn model. Of course, we need to be defensive here, and so we pass assert false, and we stop the program if a model that's not recognized has been passed. So this way, we get the best of both worlds. We can define arbitrary kinds of models I might want to use, yet we can configure them easily in the codebase. Looking at this codebase more carefully, let's take a look at how we end up passing the configuration arguments to the experiments. We have this function getModel, and we actually pass in arguments that we get from the YAML file. What this is doing is taking any model arg that might be here and you can initialize the model class. So for example, what this is actually equivalent to is we know that the model class is going to be linear regression. So this is actually equivalent to return linear regression. By using this double star keyword argument trick, we're actually able to pass arbitrary arguments that we might want to initialize this machine learning model. Let's take a look at how this looks when we're actually executing this code.
Ethan, are you able to increase the font size?
Yes, pulling it up now. Is that better?
Yes, also on the code, if that's possible.
Oh, totally, yeah. And again, if anyone's having issues viewing things or things are not clear, please let me know, and I'm more than happy to change them. Pranav, is this better?
Looks great. Thank you.
Excellent. Okay. So going back here, I'm just going to give an example how this works. So again, to run this code, we've only passed two arguments, a configuration path, a path to a YAML config file, and a base path, or a path to where any experimental log should be dumped. We run this code, and it simply it runs experiments, and oh dear. Small bug there. Okay. So we run this code, and essentially we dump a folder that we're logging to, and you can see that we've generated a new folder in experiment outputs. The way I've currently had it set up is that each experiment generates a randomly named folder in the experiment outputs directory. So you can imagine how if I wanted to run 10 such experiments with 10 different YAMLs, I could simply loop through a bunch of YAML files and generate, and then each one will get executed, generating an output directory. Looking at this output, we can see that everything important is in here. First of all, the entire code base has been copied over. So we have an exact copy of the exact state of the code base, how it looked when we executed the code. Take a look at how we do this. we actually call the simple function shutil.copy tree, which copies the entire folder over into experiment directory. Look,
Ethan, sorry, could you increase the size of the font again on the code?
is this better?
A little more, maybe.
Let me increase it further. Is this good?
Yeah, that's good.
Let me increase it also. Is that better?
Yes, thanks.
Great. I haven't zoomed with this code with Nova before, so just need to check some things. Okay, so you can see that what we're doing here is calling shutil.copy tree, and we can just call it directly on the current directory, i.e. the period. This allows us to copy arbitrary code over, essentially copy everything in our code base and copy it over to our outputs, which makes things extremely convenient for replication. Okay, let's keep going. I'm going to be back in 1 second. Okay, cool. Hello, everyone. Due to a small technical issue, we had to resume without video, but video will return shortly. Let's continue where we left off. So we discussed how to copy code and make things reproducible. We called shutil.copy tree, and we dumped all the code into our experiment directory. We also discussed how we could effectively automate hyperparameter search by simply generating a massive number of YAMLs and using them to configure a bunch of experiments. This kind of approach means that everything is easily recordable, and if there's a particular experiment you like, just write down the name of the experiment directory. The other thing I really want to point out is the way we have results stored. Here you have results like L2, mean error, and R squared. These are just saved as simple files called L2, mean error, and R squared. There's no particular reason to not name the extension, but I just want to point out that you can also totally do this. There's no rules about what extensions are allowed and what aren't. Cool, okay. At this time, does anyone have any questions about this way this code is set up or anything about making things reproducible?
Ethan, one question that comes up. So in each experiment, you're copying over all of the code. Are there pros and cons associated with that?
That's a really great question. So obviously, anything in this design comes with pros and cons, and this is especially a big one, which is why it's listed as optional on the slides. The biggest reason why it might be bad is that you might run out of space. This is kind of a problem if your code, if you have very large files in your directory, you must take special care not to copy those over. In this example, I've just obviously copied the home directory, but the base directory, but you might want to instead copy, say, just a particular folder that you might be aware of or a particular file that you need to replicate. That's the main concern that comes up usually in these kinds of contexts. But obviously for now, if you have any other ones that you're aware of, I'd be more than happy to learn more about that as well.
Oh, sounds good. Thanks, Ethan.
No worries. 1 second. Cool. Okay. With this in mind, we'll resume and go on to part 2, which is how to make your code easily understandable by both you and other people. Let's keep going from here. Cool. Organizing your code. So this is a particular favorite topic of mine, and I'm really happy to be talking about it. So what is wrong with the following workflow? This is something we see a lot. We have a Jupyter notebook. All our code is smashed into the notebook. Okay, so we might have a notebook with a section that does data processing, a section that does, data loading, a section that does model definition, a section defines all the PyTorch models, and then a plain loop in the Jupyter notebook that sort of takes care of training the model. And sort of the problem with this, like we see this all the time. And what we end up observing is that, to run our code base or to run the experiments, we simply start at the top and keep smashing shift return or whatever shortcut it is that you use, and you end up being able to write all the code. What is the problem with this? There are 2 big problems. The first one is encouraging linearity, not modularity. An easy habit here is to copy and paste code because, if we need to do something twice, okay, we just make a new cell, we run it again. This also applies to writing Python. This is also a major issue. The problem with this, of course, is that I guess everyone taught you this in CS1, but applying the same operation in multiple locations lead to tiny inconsistencies. And over time, these tiny inconsistencies become tiny bugs, which become big bugs. And eventually, your code becomes impossible to manage. Central problem here, then, is a lack of excessive linearity as opposed to modularity. This time, sorry, I'm going to have to resume dealing with a small issue. We'll be back again. Thank you. Okay, so problems with the Jupyter notebooks and common code bases. There's an easy habit. We copy and paste code. We tend to go linearly, and we tend to not really want to decompose stuff. So that's really the first big issue. By applying the same operation in multiple locations, we get tiny inconsistencies. So here's an example, motivating example that I've seen and someone I've worked with in research project, actually Pranav's group. So you have you process some data somehow, and you dump it into a train set, and then when you want to evaluate later, you then run it through the same kind of processing. And the tempting thing here is just to, rewrite this code and process it twice. What could go wrong? Well, when we have to add some slight thing to change processing, like flip the polarity or something, suddenly you get 0 performance. Then there's a problem, particularly with Jupyter notebooks, I think tends to bite people and may not be entirely aware of the underlying reason for the problem. The problem has to do with statefulness. Like, if you've ever noticed, one confusing thing on a Jupyter notebook is what is currently the case? What functions exist in their most updated form? What has been run and what has not? Old definition of variables tend to stay in the namespace in unexpected ways. So for example, if you have some variable like the data loader, and then you write some code that makes it obsolete. It's still in the namespace, so if you try to use it later, it's still available. That's a little bit weird. Again, copying and pasting code is still a problem. The central problem is just statefulness of functionalness. And I want to do a quick aside here. There's this idea about functional versus non-functional programming in that you have side effects, where a more functional style programming means that every function just passes information to each other, and there's no global state that gets mutated. Whereas non-functional, like a more object-oriented or stateful type, tends to store more information around a global state and just mutate that state to store stuff. Obviously, when we're writing machine learning code, we cannot go one way or another too far in one direction. But in general, a more functional style tends to be less error prone when dealing with these kinds of problems where you have state recurring from time to time. Let's go on to a code demo really quick, and we'll talk about KWRX after that. So sharing. Opening Jupyter Notebook. So basically, let me actually start by going over the structure of the code base that I've updated for round 2, and then we'll talk quickly about how to use it in the context of a Jupyter Notebook. So in round 2, we decided to modularize our code. So looking at the main apply that we had from section 1, we had all this code. It's very clean, decently written, but it's all smashed together into one file. And the honest truth is, when files tend to exceed about 150 to 200 lines, they start to become deeply incomprehensible to people trying to understand what's going on. This can be a problem. So what we've done in this modularized version is to split most of the files into separate modules. The overall idea is to have a separate module for each possible thing that you might, kind of action or each possible like domain of stuff that you might want to talk about. For example, here we've defined modules for loading the data, getting a model, getting metrics, and training. Each module has a set of global level functions that's performs some kind of action relating to that module. For example, let's look at the data function really quickly. The data module simply has a function called load dataset right now, which loads data from some file and does some operations. You can imagine later, say I wanted to add some kind of preprocessing. So you do that process. And you could do, this is super common if you're trying to do, say, a standard scalar or any other pre-input machine learning model, anything pre-input the machine learning process. The point here is that by divorcing everything in its own library, you actually get significantly better collaboration ability and better clarity. For one, your files are much shorter and everything is separation of concerns. So for example, I know if I want to edit the logs, I can do it without massively affecting anything from another file. Another great feature has to do with collaboration. If you're working on a large collaboration with multiple people, which is especially common in this area of the AI space, you may have a situation where, say, one person's working on data loading, another person's working on defining the model, and yet another person is working on doing hyperparameter tuning. By splitting all these operations in different files, you massively improve your experience with stuff like, the Git or any other kind of collaboration software, because now you're able to make changes only in your own file. Let's look at how this ends up working. So I don't know, just in case you've never seen it before, to use a module in Python, you simply type import and you simply put the name of the module. If the module is in the current directory, then Python will be able to import it and use it as part of the code base. Using is then identical to using a pre-built Python module. For example, load dataset, in the original file, we did load dataset, but now we do data.load dataset. Otherwise, it's exactly the same. Of course, you have to be careful not to use module names that overwrite things in the namespace. The most easy example is people adding new modules called, say, random, which makes it impossible to import the actual random. Otherwise, this code base is exactly the same. The only difference is that it's significantly easier to read and work with. The other thing I want to talk about quickly before we move on to Jupyter Notebook is this concept of decomposition. So this is in both file 1 and file 2. But you have this idea that a lot of the times you want to not only separate concerns into modules, but separate them into full functions and separate them into operations. A good rule of thumb here is that each function should do one thing. A prime example of this is this function, run experiments. A common lazy, kind of habit that people have when writing machine learning code is we dump everything into the same block on a Jupyter notebook, or we just dump everything into the same Jupyter notebook. And it's possible to tell what's going on. Rather than this, we have a different function for each operation. For example, this function handles loading the data set. This function handles getting the metrics. And when we go further into these functions, they actually decompose their own operations. For example, in getModel, we actually call getModel class from model type. This way, each function is a minimal length. The thing you do want to avoid when decomposing is doing a common habit people fall into. So people will say, okay, I have a function with, say, 500 lines of code. That's way too long. Okay, well, what I'm going to do instead is follows. Rather than typing, def main, and we have like a lot of code here, and we think this is too much code, we're going to say, okay, this is not actually helping the situation. Every time you decompose, you should actually be able to break your code by a branching factor at least 2 to 3 times. By doing this, each function at the end ends up being no longer than 10 to 25 lines. There's no point, of course, in decomposing when you just end up using the same function. Okay, any questions at the moment? Okay, I want to quickly move to talking about how to use this kind of modularity in the context of a Jupyter notebook. So here's a very small Jupyter notebook. The way this Jupyter notebook works is that it's intended as an example of how you should use Jupyter notebooks in practice. The way we have it set up is exactly the same as the original code base. We import these modules from, these modules that do these particular experiment related things from original code base. So if you run this, we've loaded in all this code. We can then use arbitrary stuff from original code base. For example, here we're loading, the data set from using the dataset.load dataset function, and we're able to run it arbitrarily. So for example, we want to load different data set. That's very easy. I can define another set of arguments, or say, I'm not sure that one's quite working right now. We can define different number of k-fold splits, and then we can call it again a different set of arguments. The point is, you're able to do arbitrary exploration in your Jupyter notebook while relying on the code they already wrote. So the rule of thumb is pretty clear here. You should always put code that might have to do with exploration, or might have to do with the underlying experiment in plain Python. The reason why is because you can run multiple of these kinds of exploration notebooks with mutually conflicting contents or different kinds of directions, and you can rely upon the same code to operate your experiments. What you should use the Jupyter notebook for is actually this kind of explorational work. Say I want to create a new data set, make a couple different data sets, look at it myself. I want to run experiments that don't quite fit into my regimented overall structure. Jupyter notebooks are great for this. A common experimental flow then is you have a bunch of this code in Python modules, and then to run the experiment for your meetings or whatever, you just, rather than using this reproducible setup I demonstrated earlier, you might just create a new Jupyter notebook and set up experimental run inside the notebook. Not quite as reproducible, but it's extremely convenient and very easy to do. But what you should be avoiding doing is to put crucial experimental code, things you might use again and again. You don't want to put that in a Jupyter notebook. I want to bring your attention also to something called auto reload. Auto reload is an extension which allows you to automatically reload code that changes in modules. This is incredibly helpful. Why is that? Well, say I want to make some major change to my code base. Let me quickly share my entire screen. Okay, so suppose we're in the following situation. I want to, by default, when I change something in my code base, I want to show up immediately on the Jupyter notebook. To say in data.py, I want to immediately multiply all x's by 100. There's no problem with that. So by default, when we do this, we have to do what I just did. restart the kernel, and then completely replace all code and memory and start again. But this can be incredibly inconvenient and take a lot of time. A better option is to use the auto reload option, because let me give you an example of how that works. At this point, then, whenever I change any of the files that it imports, the Jupyter Notebook will automatically hot reload the underlying code and be able to use it to update the current situation. So currently, you can see it's calling this function doesn't exist copy process. I can modify this, and immediately the new code shows up. It's great. So you can see that any update I make live can actually be synced to your Jupyter Notebook without having to reset the Jupyter Notebook state. This works especially well with this kind of approach I've defined, where you have underlying experiment code in the Jupyter Notebook, because I can create a Jupyter Notebook that represents a particular run or experimental configuration, and then I can dynamically edit my code and debug it while not having to reload the state of the Jupyter Notebook. The only thing you have to be careful of, the auto reload extension is kind of expensive. So in a production setting, or like when you're evaluating your models, you really do not want to be doing this. But it's really, really good for development. And of course, turning it off is as simple as commenting it out and restarting your kernel. Cool. Okay. If there's any questions about this material, please feel free to ask them now over Zoom chat. Otherwise, we're going to keep going to another important subject, quarks. Antara asks, can you kindly increase the font size? That's a great point. So I do want to let you know that the Jupyter Notebook is already available on the GitHub repo and can be used from there. But I just want to blow this up really quick so that you can see. Sorry about the font size issues. Here we just have an example of the code base just consists of importing, these modules and then running a quick function that we've derived from these modules. And the point is that you can run arbitrary functions and thus run a small experiment without having to have this regimented experimental structure we showed off earlier with the YAML configuration files and whatnot. Okay, let's go back to the slides. A quick aside I want to talk about is quarks. Quarks is a very useful trick to pass information between functions, and it's of such great importance in building these kinds of large systems that we think it should go here. A quarks is basically a way to transmit information between one function and another. So for example, if you have a quarks foo equals 5, then if the call func function defines itself as accepting some set of quarks, i.e. keyword arguments, rather than explicit functions, it can accept any arguments at all. And those arguments then dumped into a type dict. In this example, I've defined a quark foo equals 5. I have a function called callfunc that takes in some quarks, and I call it with foo equals 5. Then I can just access the dictionary option to get the data. This is great. And the thing that this is usually used for is to pass argument forwarding between functions. Let me give you a quick example of how that might work. Say we have a little, situation here. I have some function run experiment. With batch size equals 3, maybe batch equals 4, maybe like earning rate equals 1, 3. Okay. Great. Okay. And we might have some other function called okay, so we might have some situation, and this is something I found myself in many times, when you have, some kind of, function, like a run experiment function, maybe something like that, and we're needing to be calling it somewhere else. And we don't know what arguments it has. Like, we actually have no idea what these arguments might be, either because someone else is writing it, or because we tend to change the arguments every day. Like, one example, in a run experiment function might have extremely large number of arguments, and, every day we add more. And we want this wrapper to be flexible. We don't want to have to explicitly change its function signature every time we add new functions. This would not be good. The general way to do this then is to use K with W args. So when you set up KW args, we can accept arbitrary arguments in addition to any ones that we've already written. Those key KW args get dumped into the dictionary. So, for example, so calling this great. So here's an example. We're able to now run the run experiment pretty logging, set up some outer, configuration, and then any arguments don't get soaked up by this outer function, end up going to the inner one. So you can imagine you can have some really large set of arguments, and if you keep chaining these kind of KW args calls, all of the arguments end up reaching one function or another at the end. What's really important stylistically here, though, is it's considered poor style to actually use KW args at the very end of the function. So for example, I understand this is a dictionary, we're able to print it out for fun, but it's kind of considered not great style to just assume, like, do this. And the reason why is because it makes it very hard to track which arguments are left, which ones aren't. Because you can imagine people might pass all kinds of wacky new arguments that you have no idea about. And if you just use them like this, there's no effective Python defense against all these functions. So for example, right now, if I have this set up where I say, we're going to pass a run experiment, and I pass this new argument called we have a bug where we pass all the keyword arguments down. Eventually we get this argument, it doesn't exist. Oh no, we crash. But then you can imagine if all of your functions are actually just using KW args like this, which is like sort of not the best style. Let's say I did this, and I did. And it works. Wait, actually it doesn't. What is So, okay, there we go. So you can see what's going on here. Here I've passed an arbitrary new argument called we. And unfortunately, nobody has any idea that it went in because we're not being very defensive about the KW args that we're passing in. The problem here is, sure, we got all the KW args that we needed, but then also we have no idea whether users actually match the interface, which means it can pass arguments that might be a typo or not quite match what they expect, and you have no idea. The usual way to do this then is to set up something like, allowed arguments equals argument style, batch size, and insert all arg and allowed arguments or arg in each parts. So now it will complain because this arg, we is not actually found, and it's just going to crash, which again, is just being defensive and as clean as possible. Cool. So as a quick intro to Quarks, I want to give you one more example because I think it's quite important. If you look at Seaborn, say, swarm plot, I think it's a great example of how this kind of stuff usually gets up. So looking at Seaborn and categorical, there's a bunch of these very common functions. I'm sure you used all of them before. And they use KW args quite a bit to pass on additional arguments. So for example, in a box plot, we know that box plot contributes some arguments like the palette, the saturation, the width, that's all great. But then there's also this stuff like you might want to change the font size, you might want to change the axis dimensions, blah, 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 blah. And these, the person maintaining this part of Seaborn may not be aware or even care what the other arguments are. So you can tell that we want to just be able to permit arbitrary other arguments that we send over to the plotter, and the plotter can deal with handing those around. So it's basically just a good example, like argument forwarding, being general, working with other people, all good reasons to use Quarks, a really great tool, but one that's consistently abused, so felt the need to go over it really quickly here. Okay, we're running low on time, so let's keep going. Yeah, typical use case, a large function calls series of smaller functions. Don't overuse it. At some point, every argument should be explicitly verified that exists or doesn't exist, and we don't have extra ones. Cool. Cool. I want to talk really quickly about releasing because it's sort of the last major part of the equation. So now, ideally, we have a code base that's great. Everyone loves it. It's easy to read. It's decomposed, and we want to release it to the general public. The most strongest advice I can provide is that there should be no more Jupyter notebooks left. Why is this? Well, Jupyter notebooks are just inherently very prone to, again, confusion as you release them due to their stateful problems. There should really not be a lot of Jupyter notebooks left. There might be exploratory code that's totally okay. There might be code showing people how to use your model. That's great. It could be really useful to tell people, hey, here's how we deploy our model in real life. And if you have a clean pipeline in Jupyter Notebook, that might also be okay, just because that's easily replicable. But you should not involve any Jupyter Notebooks that involve people deciding where to run it. In general, like say a student, like someone just getting started in AI whose research project is to look at your code, who wants to replicate your results should be able to git clone your repo, run 1 or 2 bash scripts, maybe 3, and then after like some amount of training time or something, you should be able to get back a similar performance number. The biggest advice that I can give is that you really need to make sure this is actually true. There are innumerable research code bases where some, reproducibility code has been released and it's been trumpeted, and you run it and it ends up being 3 points lower than you expected. And there's no reason why. Nobody can explain it. It's because the author of the code did not even bother running it or verifying that it works before they released it to you. Now, the best place to fix this is the authors themselves because you're familiar with the code base. So make sure your replication works. The other biggest thing I can suggest is to document each function of the interface. And we'll go over examples of both really quickly. But the point of this process is to provide expectation invariance about arguments and return values. So the point is, if other people are trying to call your code, you should really make extremely clear how your code is being used and why. Let's go over quickly an example of a good set of released code. So this is a very small code base, not necessarily widely known. It was, I believe, an EMNLP, but I thought it was a wonderful example of a replication. So these people provide an exact script on how to use the model. They provide a simple Python code that you can copy and paste and dump into your editor. You run it and it immediately works, and there is exactly nothing left to worry about. The only major thing, of course, is you want to talk about is actually, releasing model checkpoints. I'm sure another lecture is going to go over this, but in general, because model checkpoints are too large to officially dump into, GitHub, usually you want to upload to Google Drive or to another source, and those can be downloaded later, and you can provide instructions on how to download them. Another good example is someone I've worked with before, who released a pretty popular code base in NLP. This one's also a really good example. Again, this one's a little bit more complicated than the other one because a very complicated environment is required, but they provide exact instructions on how to replicate your code base. And then there's a simple bash command, you copy and paste it and immediately works. There's nothing wrong with it and everything is exactly correct. In terms of Jupyter Notebooks, then the efficient autoregressive EL is a pretty good example of how to do that. There's a notebook here called test.ipynb, and it's just exploratory notebook. So you can see this is not, overall evaluation of the model. It just gives you, okay, we pass in some input data, and here's a nice visualization of how to run it. This is the perfect application for a Jupyter notebook, showing people how to play with your model and getting people on your side, convince them why it's a cool model. But to replicate experimental results, this is not the way to go. I also want to talk quickly about how to write a good README. READMEs should basically cover the scope of using a repo and using anything that you may want to draw from it. There's sort of 3 kind of levels of complexity here then. The first one is then going to be the simple evaluation. So how do I run the model and get back a number? That's the first one. The next one is, replicating the paper result. How do I run the model and get back whatever you published in your great paper? Like I want to get back the number. A lot of people fail to document this, which means the paper is essentially non-reproducible. The final thing you need to document is how to train the model yourself. So this can often be, it can require a lot of stuff, especially if you train it on a big GPU or something like that. The instructions may not be practical for people to replicate. Nevertheless, you should verify that it works even with a small example or something like that. In all cases, you should provide easy to run code snippets and ways for people to efficiently copy what you've done. The final component is going to be some kind of quick motivation of what the code base does, what the point is, if there's a paper linking to it, the purpose of each part of the code, which can really help the situation. Again, let's go back to one of the repos we've looked at, which can really give a good example of what's going on here. So again, I like this code base because it, again, refers a lot of the research stuff off into a paper. There's a little quick blog post that talks about how stuff works. But again, there's instruction on every level. So simple evaluation, okay, here's how you install the code. Here's how you evaluate. Then there's an example of how to replicate paper results. So scrolling down, replicating the results for some paper. Okay, here's a set of instructions, which is pretty easily documented. This is okay if it's like a little bit less clear, but it has to be complete and exactly applicable. And then finally, training the model yourself, which you simply document if you use the YAML structure that I've defined earlier. It's very easy to do that. Another good example of this, I think, is Facebook Research Blink. That's an entity linker, which means it takes data and links it to with Wikipedia corresponding entities. So we have some papers as a nutshell. Okay, use a two-stage approach for entity linking, blah, 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 blah. That's great. Here's some instruction on how to do it. So, reproducing it. And if I want to use interactively, this is a really, really nice example of how to release your code. We write another script, one that we never use in experiments, but one that just lets us interactively explore how the model works. This is super convenient because people can download the code, get it running, and immediately take it out. It's great. And here they even use color. Things are interactive. It's wonderful. Then training the model yourself, using the modeling code base. This is, again, a good example of, okay, I want to use Blink in my own code base. Here's the main functions you have to be aware of. What do they do? And that's incredibly helpful. And finally, if you have some results, it's always good to put those in the README as well, especially if your paper didn't exactly entail everything that's covered. Cool. All right. With 2 minutes left, I think we're going to wrap it up here. I want to quickly talk about doc strings. Have 257 discusses docstring conventions. Yeah, this is a good example. So I don't have a code base for machine learning here because people are often lazy about this. But if you write a function that other people are going to be using, like say, in the code base we had previously, like the load data, whatever function, it's really good to be able to document some of these arguments with some invariants or some things people should know when calling the function they might not be aware of. And this is particularly important in Python because you don't have typing information, so we really have to be careful about this. But say, we want to just be very careful and just this document anything people might not know or anything unexpected that you want to be able to document. Cool. All right. With that, I'm going to wrap the presentation. Thanks, everyone. Any questions, feel free to try contact me on my email. I'm available on my website. Otherwise, sorry for all the technical issues, and thanks so much.
Excellent. Thanks so much, Ethan, for a very wonderful presentation talking about all of the reasons and the ways that we clean up our code to get things production ready. So thank you once again.
Thank you.